What's up, Simpsonites? So we got a big test tomorrow. It's gonna be awesome. I got the study guide here to some extent. I'm gonna go over some stuff on it. Here we got types of energy. Okay, pretty straightforward. Two categories. Oh, look at that. I'm right there. So understanding what the two different types of energy are, the two major categories of energy, what makes something kinetic, what makes something potential, things like that. Heat transfer, how does heat flow? Is it from hot to cold, or is it from cold to hot? And then the three types that we did that lab with, how heat is transferred and flows between things, recognizing each of those and what they mean. Okay, so that's all pretty simple. Everything on here is pretty much directly from the notebook. I use the notebook when I make this. So, calorimetry, this is one thing I want to talk about. What type of system is a calorimeter? So I talked about this in class today, but just to go back over it. So three types of systems, okay? Three types of systems. So here's one, here's another. It's a cap. And then here's a third. It's another cap. And, oh, how am I going to draw this? I forget how this is drawn in the PowerPoint. Okay, that's like something to keep it warm or cold. Okay, so this is an open system, a closed system, and an isolated system. And we're looking at these things, we're looking at differences in their transfer of energy, especially heat, and then the transfer of matter. So the materials themselves in there. So with an open system, no cap, an open system, okay, like a test tube that's open, we can just pretend there's water in these things. And draw, here, we'll make it blue now. Water in each of these. Okay, so in an open system, if I put this on to a flame and it started boiling, that it's going to get hot. I'm going to feel that, so it's transferring energy with the surroundings. So what we're talking about here is we're looking at the system itself. The test tube is the system itself, and then everything else around it is the surroundings. So we're talking about how these things relate to the surroundings in terms of matter and energy. So energy we think of as heat. If I boiled the first tube, it would feel hot. If I touched it, it would be really hot. So that's transferring energy. Additionally, since there's no cap on it, if it was boiling, the water would start to leave as water vapor. And in that way, it's transferring matter with the environment, okay, with the surroundings. A closed system has a cap on it. So if I started boiling something with a cap on it, okay, it's still going to feel hot. It's still going to transfer that energy. If I touch that tube, it's still going to be hot. However, the cap is going to stop the water from vaporizing and leaving the tube. It's trapped in by the cap, so it's not going to exchange matter with the surroundings. Okay, so in a closed system, you're not exchanging matter, but you are exchanging energy. Now, in an isolated system or an insulated system, this is something that is not going to feel hot. If you touch it, the outside, you can see the tube is inside, so the outside is not going to feel hot, so it's not transferring energy with the surroundings. Additionally, it has a cap on it, it's closed, it's isolated, so it's not going to exchange matter either. So you have an open system that exchanges matter and energy. A closed system that's closed off from the environment, it'll exchange energy but not matter. And then an isolated system that's closed off and completely blocked from the environment, so it's not going to exchange either. That's what I'm talking about when I'm asking about systems. It's important to understand those three different types of systems. Okay. So moving on, conservation of energy. Okay, the fact that energy is neither created nor destroyed. Energy doesn't just disappear. And calorimetry is a great way to identify this because we're using a certain kind of system where any energy being not created or destroyed, any energy that's being introduced or absorbed within the system has to stay within the system. So this is what we saw when we had the hot piece of metal. We were putting in the water in a calorimeter. We saw the heat going from the metal to the water. We saw that energy being transferred, and we could measure that exactly. So that's what I'm talking about there. Which then plays into this question, number 11, asking about what we know about the energy that's being exchanged. Number 12, we get a little mathy. It's important that you know how to manipulate our equation. Oh, I didn't even know how to write it. Okay, Q, which is the energy, equals mass times specific heat times change in temperature. Q equals MCAT. So there are your 4 variables in this equation. It's important to be able to plug in things from a problem and be able to answer questions about it. Basically just solving for one variable. Okay, enthalpy. Enthalpy. So release and absorption of energy in terms of bond formation and breaking. So when a bond is broken between 2 atoms, is energy being absorbed or released? And when a bond is formed, and when a bond is formed between 2 atoms, is energy being released or absorbed? So it's very crucial that you understand when energy is being released and when energy is being formed. Okay? And you can think of that example of the basketballs on a hill. So if these balls rolled down here, so that they met in the middle, you can picture this as 2 bonded atoms. If you're going to break this bond and push them back up the hill, is it going to take energy to break them apart? Yeah. So that's a good way to think about when energy needs to be put in, and then the opposite is true for when bonds are formed. Okay. So then here, number 14, the total enthalpy of a reaction. So total enthalpy, you have that equation in your notebook, and we used it for some problems. So it's important to understand how we're calculating total energy for a system. We're looking at the products, we're looking at the reactants, we're looking at the energy that has to be put into the system versus the energy that's given off by the system. Okay? And then it's important to think of that in terms of exo and endothermic. So if you're putting in more energy than you're getting out, it's endothermic. Overall, that reaction is absorbing energy. If you're releasing more energy than you put in, overall, it's exothermic. Overall, that reaction is releasing energy. So we use this equation, the equation for the total enthalpy, to assess whether or not energy is being released or energy is being absorbed. And we see that in whether the sign is positive or negative in our answer. So that's how we can assess whether or not energy is being absorbed or released overall, and it's endo or exothermic overall. So for this stuff, for enthalpy, it's important to understand the big picture of bonds being formed. So when you have a reaction, I did this on the board. Let's just make it a single replacement, it's easier. Okay, so these are both going to be 0. I don't know if you're familiar with that symbol, but I'm just, any element by itself, the heat of formation equals 0. Okay, and then for these 2 compounds, there's going to be a heat of formation and the heat of formation, which is going to be positive or negative depending on it's formed or broken. Either way, so I have to put, it's going to take energy to break this apart, and then it's going to take energy to put this together. Okay, and I have other videos on this, I believe, at least one. So when we're doing this reaction, we're looking at how much energy do we have to put in to do this, to break it apart, and then how much energy did we get out when it was formed, when the products were formed. And if it took more energy here to put in to break this than we get out when we form that, this is going to be an endothermic reaction because overall I'm putting in more energy than I got out. Now, if it takes less energy to put in than I get out more energy, it's exothermic because overall I'm releasing more energy than I put in. Okay, so that's where bond breaking and bond formation tie into the total enthalpy of a reaction, whether or not it's endothermic or exothermic. It depends on how much energy you have to put in versus how much energy you get out. More energy out than in, exothermic. More energy in than out, endothermic. And that brings us to our potential energy diagrams. So let's see, I'm going to skip ahead to this because it plays off better, and then I'll go back to that. So when you have a potential energy diagram like this, okay, so these are your reactants, and these are your products. And on this side, we have energy, okay? So the reactants have less energy than the products, and I made a video on this, the in-class video. I talked about this a lot. We see that overall, we put energy into this system to go from here to here. We put energy in. The products have more energy than the reactants. Therefore, this is endothermic because we're putting in energy overall. The whole reaction, at the end of the reaction with the products, we have more energy than we started with the reactants. Okay, so that's what I'm talking about here with the put in versus get out, and we see that here. Okay, so how's energy release absorption different? So exothermic, endothermic, which one's absorbing, which one's releasing? And how do the energy of the products and reactants differ in endothermic and exothermic? So when you're looking at a chart like this, I just said this is endo because the products have more energy. What would an exo look like? All right, and then I like this question. Is endothermic or exothermic more likely to be spontaneous? So when you're thinking about this, think about how difficult is it to start an endothermic reaction versus an exothermic reaction, and look at the charts like this. So this is that's what an endo looks like. An exo would look like this. Okay. So what on this chart? What aspect of this